Alright, so again, setting this up dy dx makes this an integral if I get my boundaries right that I can do. If you set it up dx dy and you can work it out, show us how to do it. You can present that in class. I'll give you some extra points because that is not an easy integral. You can type it in your calculator, but that is not an elementary integral. It would require a little research. All right, let's see if I can find another problem, another volume problem for us to try. I'll give you one. Let's do one that has the surface already drawn, because that definitely makes a difference. Kind of helps you set the boundaries up if they're not given to you already. All right, so let's see if we can figure out how to find the volume of this figure. Remember, z equals f of xy. Now, with this given information, I'm sure that there is more than one way you could set this up. However, you may want to try to visualize what that would look like if you were looking down on it in 2 dimensions to help you set up your boundaries. How would this down here look like if we were just looking, we weren't looking at the thickness, weren't looking at the z component, we were in our 2D land, right? We just have height and width, but we know nothing about, or no, we have length and width, but we know nothing about height. I mean, that would help you to set up your boundaries. So we have the line y equals x. Of course, we're just in the first quadrant here, first octet here. And then we have the line y equals 2. So this is the bottom of the figure. If we were looking down on this figure and we could tell nothing of the shading to give us the height, you know, in 2-dimensional land, that's all that figure is. The integral is definitely not going to be tough. So I'm sure we could set this up dy dx or dx dy. But remember, the outer integral needs to have your x boundaries. or your y boundaries, and they need to be constant terms. Okay, so we know what our function is. We know that we have 4 minus x minus y. Now, do we want to try to work this dy dx or dx dy? Anybody? Dy dx? Alright, so let's see. Dy dx. The way that I worked this out, I worked it out dx dy. So, no. Let's see if we can set this up right, dy dx. So, whatever we plug in, remember when we integrate with respect to y, we're going to plug in for the y and get rid of the y terms and make them x terms. So, if y equals x, then how are we going to set this up? Just change it. Did anybody work it out dy dx? And what were your boundaries?
I used x and 0.
Did you go from 0 to x?
Yeah.
0 to x. Okay. And then what were your, so we have to use x boundaries on the outside. So what did you use for it?
Oh, I did it wrong. I used wrong values.
But
You use 0 to 2?
0, how do you know 2? Is that 2 right there?
Yes,
0 to 2. Well, it's y equals 2, but and then x equals y. So let's see. Let's see if this works. I'll compare this to my answer. I haven't worked this out this way, but we'll see. So it's going to be 4y minus xy minus y squared over 2. And then we have to evaluate this from where to where? 0 to x. And we're plugging this in for y. So we're going to have 4x minus what? That'll be x squared when we plug that in for y. Then minus x squared over 2. And then when you plug in 0 for y, you get 0. Now, you could put those two terms together. They're like terms, right? You don't have to, but that would be what? Negative 3/2 x squared. Now, let's integrate that with respect to x. So that'll be 2x squared minus, now whenever I divide by 3, that's multiplying by 1/3, that's going to make that term what? 1/2 x to the 3rd. Evaluated from 0 to 2. Alright, so this is 2 times 2 squared minus 1/2 times 2 cubed minus 0 and 0. 2 times 2 is 4 times 2 is 8 minus 1/2 times 8. Well, that's got to be half of 8. But that is 8 minus 4 is 4. So you did get the same answer that I did. And we set the boundaries of integration up differently, or the order of integration. So we could have set that up dy dx or dx dy. It's just if you set it up dx dy, you need to integrate from 0 to y and 0 to 2. And everything ends up very similar all the way down. Do we need to do another one, or are we pretty good on that? Do we need to do another one? One more? Do we want to do an easy one or a hard one? Make it last a while? I'm wondering why you would want that to last a while.
Do a hard problem really fast like this.
Hopefully this won't be too tough. I'm just picking a random problem. I could give you another solid figure like that, but they all basically work out the same way. You just look at the figure and set up the boundaries. Huh? Alright, so let's set up and evaluate a double integral to find the volume of the solid bounded by the graphs of the equations. We're going to set up and evaluate a double integral to find the volume of the solid bounded by the graphs of those equations. Alright, so can we solve for z easily? So if we did solve for z, we'd have z equals 1 minus z squared equals 1 minus x squared. So z equals the square root of 1 minus x squared. And that is plus or minus. And then very similarly, we would have z equals plus or minus the square root of 1 minus y squared. Now, if z is equal to both of those, then we should be able to, those two are equal. I'm trying to think of the figure that this would be if we had z equals the square plus or minus the square root of 1 minus x squared and plus or minus the square root of 1 minus y squared. Can you tell from that equation, from those two equations, that y is equal to x? Most definitely. Because since these two equations are both forms of z, then y should be equal to x. Or, yeah, y equals x. Now, a lot of times when we have plus or minus a square root, it's like we have maybe one side of the circle and the other side of the circle, or one side of the figure and another side of the figure. So we might be able to use symmetry and work it out with just the positive square root of 1 minus x and say our integral times 2. You know, just like if I was, and I'm going to erase this, so don't write this down, but if I was wanting to find the area under this curve, if I was wanting to find the area here and here, well, this is represented, if this was, say, y equals 2 minus x squared, if I solved for y here, I would have x squared equals 2 minus y, and x equals plus or minus the square root of 2 minus y. So one of these sides is the positive square root of 2 minus y, and one is the negative square root of 2 minus y. And so if I used one of those and figured out the area of one side, then I could say that times 2 and get the area of both sides. Well, that's kind of what we can do here, except we're dealing with volume. Since we have the plus or minuses, we can set it up and say it times 2 just using the positive. Okay. All right. Now, we need to think logically here when we set up our integral. We know that we're going to say it times 2, but and also if we can use either one of these. It doesn't matter. But I'm going to use the square root of 1 minus x squared. Now, is that an elementary integral? I'm not saying that we can't do it, but can we do it very quickly? If you can do that integral very quickly, then show me how to do it real quick. I mean, maybe we can use some kind of trig substitution and do it, but it's not something that we could do very quickly. Now, what would happen though if I integrated that with respect to y first and then respect to x? Well, when I integrate with respect to y, if I set my boundaries according to x, then that's going to give me a y in front, which is then in turn, when I evaluate my limits, I will get an x in front. And x times the square root of 1 minus x squared is an elementary integral. It's just a u substitution integral. So if I set this up, and remember x equals y, so I'm going to set this up from 0 to x, and then I'm going to have to use, remember, my outer boundaries are both going to have to be constant values. So if I take this equation right here and I let z equal 0, then what will I get for my x boundaries? I would get plus or minus 1, but remember I'm in the first octant, so that's 0 to 1. Now, and that's not as important as this is here. If I did want to set this up dx dy, I would want to have the square root of 1 minus y squared here, and I would want to be integrating from 0 to y. Anyway, I'm integrating with respect to y first. So that's going to be 2 times the integral from 0 to 1 of y square roots of 1 minus x squared evaluated from 0 to x. And so now that's going to give me the integral of x square roots of 1 minus x squared. And so if I let that be my u, what's under the radical there, my du is present, and I just need to adjust for the constant. And so if I bring out a negative 1/2, then that's going to be the integral of what? U to the 1/2. So that's the negative integral from, well, let's go ahead and integrate. That's the negative of, what's that going to be? 2/3 u to the 3/2 evaluated from 0 to 1. Now don't do like I've done before and plug the 1 in there. Alright, remember that's u to the 3/2, so you have to go back and you have to plug in your u, which we let be 1 minus x squared. Alright, so that's negative 2/3 times, what do I get when I plug in a 1? 0. Minus, what do I get when I plug in a 0? 1. Alright, so that's negative 2/3 times negative 1, or 2/3. So 2/3 cubic units. All right. So I'll make sure that you have enough to practice on your homework on these, so that you can set up some double integrals and get some volume. The main thing that we can do is the double integral. So I mean that's like the main topic, but then you can use it to find volume. And of course if you can't do a double integral, then you can't do a volume problem. And we can use triple integrals to find volume as well. We'll do that in the future. So I will probably give you more double integral and triple integral problems working out the actual double and triple integral correctly than I will volume problems on the test. Not that it's not important. I may give you one volume problem, but I will give you more double and triple integrals than I will volume problems. Probably 2 or 3 times as many. Because that's the main thing, you know. I had a student last year that I saw at a football game, and he said, well, we're just starting to use double integrals. And he was a civil engineer in one of his classes. He said, I sure am glad you taught us that. I was like, well, I have to teach everybody that, but I'm glad you learned that, because he was having to use that to find things. Now, we just have a couple minutes left, so I'm just going to have enough time to introduce the next topic, and probably just, you know, just have a little time, like I said, not much. And this is change of variables, polar coordinates. So you've seen how setting up the problem correctly and when I say correctly, I mean setting up the problem so that you can integrate correctly is a very big deal, because if you don't set it up right and you can't integrate, then it's no use to you. One way to actually make the integrals easier sometimes is to change them from rectangular to polar equations. And if we change an integral from rectangular to polar, that can make it a little easier at times. The big difference is the dA that we have, the differential that we use, dA. Like we have the integral of f of xy dA, and it's a double integral over some region R. We were setting that up x dy dx or dy or dx dy. When we change that over to polar, that f of xy is now going to be f of, well, what is x in terms of polar? R cosine theta. What is y equal to? R sine theta. And that changes our differential out here. It's not dy dx or dx dy. It would then become r, that's a variable, r to the first power, dr d theta. So that is the differential that I use when I integrate, and it has a r to the first in it, which is kind of different. And then of course that's going to change our boundaries. Now we're going to have a dr. That's going to be some length, some function of theta. And we're going to have the outer differential here is d theta. So that would mean that the outer here would be angle measures. Okay? And that's what we'll start working on Wednesday.